Okay, hello everyone. Great that you came. I would have felt very strange to be here alone. We're going to talk on sustainability by the numbers, and today's lecture is like an intro to get into things. So it's all about back of the envelope or street fighting quantitative reasoning. Okay, which might, first I see some smiles, which is good, and also it might be a bit abstract. And in general in the course, in order things not to be just words and abstract stuff, we try to do some active learning that goes through examples. Okay, that's the spirit, and I think from what I learned, this is a good way to learn. Okay, so I didn't say I'm Ron Milo, you probably guessed that, and together with me we have the teaching fellows of the course, Lior, Liad, and Sam that you're going to meet that is now abroad. And the first question that I'd like to start with active learning is the fact that, I'm teaching this course. I think it's really useful for all sorts of things. Quantitative reasoning could get you into, win a job interview, but also enable you to do good research. And I would say that especially today, it's also extremely useful as kind of like a bullshit detector. Like if you want to be able to tell if things that you got from, I don't know, some AI tool, or just that you read in the news, whether it makes sense or doesn't make sense, whether it's true or not, I think this course could help. And in that respect, I think the course is useful not just for the students here, but also, I would like it to be much more widespread, those capabilities, which made me very curious when I got an offer to do this as what's known as a MOOC. Somebody knows what a MOOC is? Yeah, what is it?
Is it like an online, lomda?
Right. It's an acronym for Massive Open Online Course or something like that, or maybe I'm Open Online, Online Open. I don't remember. The thing is that it's a way to reach a lot, and therefore I had a dilemma. Should I turn the course into a MOOC? Also, what are the advantages? Everybody could reach from the internet, millions of people, etc. And that was quite exciting. And so I said the first thing when I want to experience such a thing is to try and do it myself. So, I did it online. There's this thing called edX, which is, combination of Harvard, MIT, some other universities. And I did that. It was kind of fun. I've learned a few new things. And then I got an email from them at the end of the year. And I want to share that email with you. So it's kind of like an end of the year report on, everything they achieved in that year. And I'm curious to see what you will think about it. So I suggest that you open your email, like your inbox, and check in what's in there. If you didn't, I think you'll see the email already. If not, just join somebody else. Maybe there's some problem with your email did not arrive or something like that.
Maybe it will take a second.
Maybe it will take a second. So maybe while we're waiting that second, anybody sees any other reasons why you... Okay, I see people smiling, so you probably have something. So the idea is to try and look at what you got. Maybe it's also good to discuss in pairs if you're next to somebody, and to try and think, should I convert this course into a MOOC, like invest the time and the effort to do that?
No. The numbers make no sense.
Just for a second, take your time. It's good that each one thinks for a few minutes.
It's just the numbers.
Can't really relate to those numbers.
Okay, so let's start with just the bare facts. So what do you read there? Somebody could remind me some of the things that they sent. So this was like end of the year. Yeah.
Free media
33 times 10 to the 6 enrollments.
239
Oh,
million
fuck.
minutes of
Sorry.
video watched.
Somebody gave me a permanent. Um, I think we have ethanol. Let's use it straight away. Expect the unexpected.
Oh wow.
Magic.
That was amazing.
As they say, science is magic that works. And in this case, also chemistry. Okay, stay with what you know. This is, yeah, these.
The other ones are okay.
Okay. Okay, so 66. 66 million enrollments.
33.
33. What else do we have there?
230 million minutes of video watched.
230 million minutes watched. Yeah.
120 million problem sets attempted.
Problem sets. Anything else there?
1,300 courses from the world.
1,000 and
300.
300 courses. Okay, good. So as you can tell, this was like an email that was, coming to say how much they achieved, right? It's something very often done, with big numbers. It's very impressive, and then people are impressed, and then they get what they want. Any thoughts about what you can infer from those numbers? Yeah.
You can, if you deduct like 2 or 3 days, like if you assume that every course got around the same enrollments, minutes, problem sets, so you can just divide every number by like 10 to the power of 3. So then you can say per course you have, let's say.
So you're saying you could divide this by the courses and see
Yeah.
per course what
Yeah.
we got there. Okay, so that's one direction you could do. You had another direction?
Just add the population of the Earth as another number and see what fraction of humanity has enrolled to those numbers and suspect if it's true or not.
Okay, so you're saying, you can compare this to the population of the Earth. I always like putting context, so that's some interesting context. Yeah.
I hope that I don't know, but it seems like if you divide 232 the enrollment, it seems like every enrollment watched it 7 minutes.
Okay, that's something which I want to go a bit further with. So you're saying this is the number of minutes. This is the total number of people, right? And you're saying let's divide the two numbers. So if I take 220 million, I divide it by 33 million, I get what?
Around 7 minutes.
7 minutes, let's make it 10. In general, you might see that you might have some knee-jerk reaction in this course that for me, 7 is equal to 10. Okay, and don't feel too bad about it. So 10 minutes per student. Which means that either they're like super, super smart, they really learn, so much in 10 minutes, or I don't know. So you can say, of course, there's a distribution here. With distributions, there's people, very short, very long, etc. But it automatically, just 1 second, automatically tells me that this number of students or enrollments that, sounds very impressive, I'm already much less impressed with it. And see how it was actually very easy. You just have to divide two numbers. Yeah.
Yeah, I think with numbers, it's interesting to see what numbers they did not present. So I think what is the enrollment? Yeah, okay, but what is the number of students that finished the course?
Okay, so there's numbers which are not shown here. That's correct. and that would have been information I would have liked to know. But now I'm trying to see what can I do with the information they did give me. Okay, any other inference you want to make with this?
I think the problem sets probably represent the most investment, so maybe we should take a look at that.
Okay, so problem sets also sounds very impressive. 120 million problem sets. Like, we're going to make you work very hard. What?
Attempts.
Yeah, so you're going to work very hard in this course. We'll give you also, every week basically we'll give you an exercise. We think it's important. That's part of how you actively learn and, make a difference with it. But, usually it comes up, an exercise following, like a 2 hours lecture. And then, it's pretty effective. What's happening here? We can see how many problem sets and how many minutes, right? So again, now you can divide this by that. So you can do 230 million minutes divided by 120 million problem sets. And this is about, we can make it 1, but let's make it 2. And this is now minutes per problem set. Which, I've been talking already way more than 2 minutes. I'll give you a problem set, but, it would have been pretty intense every 2 minutes a problem set. But maybe it is part of just, verifying you're alive. That's fine. I would say this is, more interesting and worrying for me. Okay. So I think this, yeah.
Sorry, but I thought that the data was that those are problem sets attempted. It's not the amount of minutes they spent on each problem set.
You're right. I think this is like, this is like on the average, every 2 minutes, you have an attempt. Attempt is like usually they give you, they teach you something and then they give you to do a problem set.
Wouldn't someone watch a course and then attempt the problem set after watching the video?
So they intersperse it within. It's kind of like I'm trying to do active teaching. So, I'm asking you questions already now, not just as an extra in the end, but just already throughout. Okay, so let's take one last. So this is, already tells me, the people that, that would, if I do a MOOC, they'll have a bit of an attention deficit maybe in terms of how long they spend on the course and things like that. But you might say, still it's a lot of people. Maybe it's still worthwhile because, the number of minutes still sounds, let's just talk about number of minutes, still sounds quite impressive, hundreds of millions of minutes. Is it? How do we know? So whenever you have you find a big number, in order to make sense out of it, you want to put it into context somehow. Okay? What context could be relevant? How would you? I need to massage it somehow to get into something that would give me some context. Okay? Yeah.
You can divide it by the number of courses. Then you will get minutes per course.
Okay, so here's a suggestion. We'll start by dividing minutes per course. Okay, so I have 230 million divided by the 1,300 courses. So that is roughly what? This would be about, this divided by that would be about 0.1, 10 to the 6 minutes per course. Okay? So we have about 100,000 minutes per course. What do you think? Still a big number.
What's the average time of each course? We can try and understand how long is this course?
Great. So in order to put it, I like this idea. In terms of putting it into context, you're saying, okay, let's take a normal course, something we sort of understand, and try to use that to turn it into normal courses. Okay? So how many minutes would you spend? Yeah?
So this course, just watching it at when it's 100 minutes times 14 weeks.
Okay. So now we're opening up and we're saying, okay, this course. Okay, so we'll get to it in a minute, just 1 second. So we're saying there's about 100 minutes, let's say, per lecture, and that's times about 10 lectures per course. Okay, so it's about 10 to the 3 minutes per student. You are with me? Yeah. And you were saying?
This is per one student?
This is per one student. One student coming to, spending here 100 minutes, and then 10 times we'll meet,
Yeah,
roughly.
but the first includer is per all the students.
Exactly. Okay. So this is in total. This is per minute for a normal student, normal course, etc. So this is nice. This is what I think you were alluding to always at the beginning. Now I can divide this number by that number, and then I can have 10 to the 5th minutes per 10 to the 3 minute per student. It means that this is effectively like 10 to the 2 students. So what does that mean?
This is assuming they finish the course. They see only 10 minutes of it.
Yeah, okay. So right, so it's like you have here students that came, most of them just watched, a minute or 10 seconds or 5 minutes or something like that. There are ones that went throughout the whole. So it's a mix, but it shows that on average, the course that, that if I do that and invest all the time and effort, effectively the number of students I would have, usually in this course we have about 50 students finishing the course. And this is not very different from this. Okay, so even though we started with like millions and something looks super impressive, it's all over the world, maybe like in Southeast Asia, you're expecting that like millions of people would be watching it. It turns out that on the average, it's kind of like a course here. And it has all sorts of other properties that we're not getting into right now because we're just doing the average view of exactly how much of attention deficit they'll have. Is it just short or long? The fact that in terms of interaction, it's a completely different thing. But also in terms of like if you look at the distribution, if I'm thinking about giving this course, how is the distribution important? What do you think?
It's more standard. Like if we do it frontal, most of the students come to this close to the same number of time and they invest the same energy. But if you're doing it online, it's like more wide distribution.
Okay, so this is one aspect, and that's like if you look at the distribution of how much, what would happen with the students in terms of engagement, etc. That's one thing. This is actually all, okay. What any other issues that you see about like, or interesting point about the difference, yeah?
Like what's the differences between the best course that has the most students and the least best?
Excellent. So I think that's an important point. And this is all part of quantitative reasoning, okay? Like we did the, what's called as a first order, like, just taking the averages and finding what can you infer from that. That's useful. But then there's another thing. If you think about these 1,300 courses, if I'm adding another course, what should I expect? I could expect it to be just an average, another one added. I probably think that it would be better than average, of course, because I'm better than average. But it's good to know a bit more about it. And I think if you look at those courses and what are the you might have heard or people usually tell we have millions of students in the course that finished it or whatever. Yeah, this is like some people are giving a course on introduction to AI or linear algebra, the lecture from MIT. Excellent speakers, also a course people have to take or that you want to take it for a year. So the distribution is such that out of those, there'll be like those that are extremely popular, usually all sorts of things like 10% of the course is taking 90% of the attention, and then you have a long tail. And even though I think I'll be one of the top, probably not. I'll be in the long tail. Why? Because I'm not teaching intro to AI. And something like that. So given that, it might even be worse than the calculations that we did in terms of the average. Okay? So short summary. I decided not to turn it into a MOOC because it's also a lot of investment of time. And now I understood that what I'll get, I'm not sure that it's worth it in terms of of what I'll get. Also in terms of the interaction, it's not the same effect. And I think more interestingly for you guys is that I was sent this by, really smart people, both working in marketing. Actually, these are also professors, that they were doing this in those excellent universities, coming to impress. I think it shows us how actually there's a low-hanging fruit here in terms of quantitative inference, that if you come with the right frame of mind, that you're not taking numbers just as decorations, which often happens, like you put a number and like people are just taking it for granted, but actually you're trying to use it as something, as a tool that you can look at and analyze. You can get sort of like a sixth sense, like another very super power, I don't know, like you're a superhero that now you can infer things that people, it was available to them, but they just did not notice it. Okay, and hopefully by the end of the course you'll feel that you have that capability. Good? Okay, so I think we talked about this, we mentioned that. Okay, now everything that I'll be doing is very much not only, this way of trying to approach problems, as started way before I started giving this course, and there's like really one of the heroes of science that was very using this sort of reasonings a lot. His name was Enrico Fermi, and often the sort of thing of like doing these back of the envelope calculations is also known as Fermi problems. Anybody has heard about such questions or knows about examples of Fermi problems? Yeah?
Maybe something like how many gas stations are in the US or something like this.
Exactly. How many gas stations are in the US? That would be one example. Any more examples? So the classic, just one second, the classic example that, is that Fermi is about how many piano tuners there are in Chicago. So Enrico Fermi fled from Italy to the US, and then he was a physicist in the US, and therefore, in Chicago, and therefore he would give that question. And, it might sound like, out of context, but, if we really wanted, we could infer this as an example. Yeah, so let's see if you could think about more such examples.
Is there one of the windows in New York City?
How many windows there are in New York City? Yeah. Anybody knows any other fun ones? So, in that spirit, but I think piano tuners maybe are less common in our intuition and what we're looking for. And I'm not guessing that in the next job interview you'll get after you finish, they probably would ask you more about the gas stations in the US than about piano tuners. So let's take something that's close to my heart, and I really like hiking. And so let's consider if I really wanted to do a really serious hike, which would be, to start, where should I start? Let's start somewhere at the equator. And let's say I wanted to walk along the equator until I reach the equator again. Okay, like to walk around the Earth. It's kind of like, it's a tough trail. Here in Israel, we have the Jesus Trail that leads, from Tiberias to Nazareth, or the other way around. So this would also be kind of like a global Jesus Trail, if you like, because, if you do that, you also need to be able to walk on water. But let's say I wanted to do that. How long would it take? So that would be our Fermi problem, and it's good to first test our intuition. Okay, so let's give some options. A, it would be somewhere between day to week. B, a week to a month. C, a month to a year. D, year to 1 to 10 years. (10 to 100 years). F, It depends. Okay. Question is clear?
What is the train?
Yeah, it's here.
What is the?
From. Okay.
The
No
Galilee
Galilee
to
slide, okay.
Nazareth.
No. So I'm not talking about the trail here. So yeah. So I'm sorry, I wasn't clear. How long will it take to walk the global? Okay, so we're starting a new fad here. I think it will become very popular. You start somewhere around the equator and you walk along the whole equator. You circumference the Earth until you reach the same place. Okay, and the question is, how long would it take you, assuming you were also able to walk on water? Okay. What?
Is your pace of walking on water similar to your pace of walking on land?
Yeah, so let's say, great question. You walk, tirelessly on land and water. Okay, I see people are already making plans.
You need
Uh,
to see.
What is your pace?
What is your pace? I don't know, whatever is your pace. So, the reason I gave, a range of values is in order not to be very accurate, whether, a bit faster or a bit slower. It's like, whatever you expect
But is
of you.
it just walking, or is it like walking day and night, or?
Or are you resting and eating and
Your choice. It's within, if you're a serious hiker, it's a factor of 2 or something like that. So a factor of 2 would not change the result very much. We'll talk about those things. Okay, question is clear. So before we go more deeply, it's good to also, one thing you'll find that, we're trying in the course also to improve your intuition. Okay? Because if you want to do street fighting quantitative reasoning, sometimes you don't have a piece of paper and a pencil and half an hour to think about things. You want to also have good intuition because that's also enables you very quickly to interact and to think about things. So let's test your thinking. Who's voting for somewhere between a day and a week? Yeah, nobody is that optimistic. Between a week and a month? Nobody. Month to a year? Raise of hands. 1, 2, 3, 4, 5, 6. Let's make it 10. 1 to 10 years. Okay, I have half of the class. 10 to 100 years. 1, 2. It depends. Okay, I have 5 people. Okay, 5 people get out of the class. It's not, we're really looking for people that, I don't know what reason you thought about it depends, but, it's very easy to fall into it depends. We do it in biology at least, all of the time, almost for any question. And again, I'm a bit, taking it not seriously enough. Of course, sometimes it does depend. There's also some fine issues. But I think for that, I think it's fair enough, that you'll be able to risk yourself and come up with an inference here. So far, so good? Great. Okay, so how do we approach this? It's, yeah.
You need to calculate the distance that you have to walk.
And then?
And then you need to know the pace that you are walking in. And just divide and find the time that it will take you to do it.
is
Right,
that
so-
question
How
to
much you
train
walk a day?
live from one profession and walk?
Okay, trains is a much more advanced subject. We just, we started with walking. After you'll show me that, you're really good. Okay, so what was suggested here is the simplest way of what's known as divide and conquer. That you take a problem and you break it into parts. Here it's kind of trivial. Okay, you want to know the distance. You want to know the speed. You divide it, you get the time. Okay, so far so good. We'll start with the distance or with the speed?
Speed.
I'll start with the distance. Okay. So what is the distance that we need to walk?
40,000.
Okay.
2 pi, the radius of the Earth.
Okay, so there's a few ways to do these things. One is, if you need to know something say, the distance here, the circumference of the Earth, I would say generally there's 3 ways to do it. One is that you know the answer. So somebody said the number, what is it?
40,000. Yeah.
40,000 kilometers. How do you know that?
I asked ChatGPT.
Great. Okay. So that's one approach to get the answer through asking ChatGPT, or just know the answer from anywhere else, and that's legitimate as long as it's true, etc. Although I would say for the fun of the course, I think it's better if you don't use the ChatGPT on the course, because for all sorts of reasons, I think you learn much less. But there's a fun way also to know that, by the way, that it's 40,000 kilometers, irrespective of what ChatGPT says. And yeah?
I assume you can calculate from the day has 24 hours. Right.
Maybe there's also a cool way to do it that way. But there's actually something that I've learned. Actually, I've learned it in the course, so I'm really happy. Also, I'm teaching and I'm also learning. And whoever teaches me something really cool gets a bonus. I will tell you that.
Can you switch a marker, please?
Yeah. So they actually, thanks for pointing out. So they taught me that the way, so what is 40,000 kilometers? That's 40 million meters. Now that's a very round number, that's a very round number. You could say, it's not exactly, that's just, and we're doing rounding all the time in the course, so that's completely legitimate. But it turns out that it's actually supposed to be exactly the number.
Yeah, the French Revolution, after the French Revolution, they do men's work around, but they didn't do it was not that accurate.
Okay, so every story that starts with the French Revolution is a good story. Sometimes it's true, sometimes it's not. In this case, I think it's actually true, which is a special, special bonus. So it turns out sometime after the French Revolution, they decided to redefine the meter. Okay, to decide how to define the meter. And the way the meter was defined was that if you started from, from the equator until the pole, you define that this distance, that 1 meter is 1 over 10 million of the distance equator to pole.
Maybe that's why it looks like the radius.
Yeah, it's not so, I didn't do it properly. It's like, how do I do it properly? I don't know. Something, maybe the other way around would be clear. Yeah, whatever. Yeah, as you see, my painting still requires some improvement. But the point is, just one second, the point is that the meter was defined as 1 over 10 million, the distance from the equator to the pole. Okay, which means that the whole circumference is going to the pole, from the pole back to the equator, the other side, then to the other pole, then back to the equator 4 times, 40 million. Okay, yeah.
But I just wonder, isn't the Earth not a perfect sphere?
No.
So, and I don't know what's the convention, but usually when I think of how long the circumference, I think of the length of the equator itself, right? I think it's more like the picture that pops up in people's head if we talk about what the Earth looks like. We don't think going from South Pole to North Pole, right?
Yeah. Okay. So first of all, you're right. The Earth is not completely spherical.
Yeah.
It's more of like an egg, although I tend to forget it because of that centrifugal, whatever. It's a bit more like this or a bit more like that. The point is that, it's true, but it's negligible. For, we're doing we want to know the answer at this level of resolution.
Yeah.
So if it's 10% more or 10% less, I don't worry. That also answers the question if I go to the pole or if I go along the equator. Again, these are all minor effects in terms of quantitative reasoning. Okay, good. So this was just a fun comment. It's really not the essence. The point is that one way is to just know the number. Okay. A second way is to calculate it. And when you calculate, how do you calculate it? Somebody said before. Yeah, so you need to know the radius of the Earth. What would I do? What color did you like? Maybe this would be okay. Okay, we have the radius so good either. Just 1 second. Aha. Red you didn't like either. I'm out of colors. We have the radius of the Earth and the equation for the circumference, 2 pi r. Okay, so method 1 was to know the answer. Method 2 is to use, to calculate it. But then you can calculate, I would say, second way is to calculate it roughly. What is roughly? You need to do 2 times pi times, what is the radius?
6,400 kilometers.
Okay, 6,400 kilometers. Good, so how much is that? You can calculate exactly, but I would say a second, like another way to do this is to calculate with what's known as 1 few 10 algebra. Okay, what is 1 few 10? If you need to do a calculation, you can, you can just work with kind of like orders of magnitude, which is the 1 and the 10. But sometimes you have something which is a few. Okay, what is a few? If 3, 4, something along those lines. And the nice thing is that you can solve things if you just know that few times few is equals to
10.
Right, to 10. So with that you can infer a lot of things. Let me play around with it just a little bit. So if you want to do, say, this calculation, so you can first say, I have the 2 and the 6,400. I can multiply that. It would give me 2 times 6. It's about 10. So I would have 10 times 10 to the 3 times pi, which is a few. I'll write it as f. So I get few times 10 to the 4 kilometers. Okay, and you can compare this few 10 to the 4 to this 40 million. That's kilometers. So if you want to turn it into meters, few times 10 to the 7 meters. Okay. Think about it. Maybe you like it, maybe you don't like it. We'll see where it could come up handy. And then you can finally just do the calculation itself. So if somebody opens a calculator, they could do how much is 2 pi times 6,400?
Yeah, I hate to say numbers.
What?
40,212.
40,212. Or just let's leave it at kilometers, otherwise it's really ugly. Good, so we have 3 ways to do it. Everything comes up to roughly the same. Let's move on. We have the distance. Now we need to talk about the time. Excuse me, let's talk about the speed. So, what do you think about how do we infer the speed?
So when people run for about an hour, they do like 10 kilometers. So a few times 10 kilometers is a reasonable amount to do for a day.
Okay, so we could do it through running. Okay. Any other suggestions? Yeah? Somebody, yeah.
You said national today is around 1,000 kilometers in 2 months. Then you can multiply by 40.
Okay, fantastic.
People walk around 10 to 20 kilometers a day while hiking.
20 kilometers.
I know that my average pace is about 3 kilometers walking. I know that I can walk about 8 hours a day. So now I walk 24 kilometers per day.
Okay, so we had several suggestions. What I've heard is that people talk about doing few tens of kilometers per day. Okay, that sounds about right from all the different methods with the running, with the multiplication, with the 10,000, with the 1,000 kilometers over 2 months. Everything converges to something around that day, around that time. Good. So if we now have the total number of kilometers or meters, kilometers, and we have this, we could just do the division. So the time would be few times 10 to the 4 kilometers divided by few times 10 to the 1 kilometers per day, which gives me how much?
10 meters.
Few falls with few, 10 to the 4, 10 to the 1. So I have 10 to the 3. And what are the units? Kilometers, kilometers cancels. Days was divide by divide. Days. How much is 1,000 days?
3 years.
So we definitely here, which I think many people could be proud of their intuition. Some people will still improve their intuition. All good either way. By the way, there's another fun way. So this is all good. I have to say I did it differently a bit. And that was when I thought about the speed. I just remember that, like, you know, again, something that like a person usually walks at around 1 meter per second. Okay? And there's another fun thing if you think about time, and that's if you think about the number of seconds you have in a year. Okay, how do we do the number of seconds in a year?
Per minute, per day,
Yeah.
So we have 60 seconds per minute times 60, again now minutes per hour, times 24 times 365. Right, this is number of seconds per year. Okay, if I want to see how much does that amount to?
That's pi times 10 to the 7.
So let's see, we could do 6 times 6, that's 36, times 10 to the 2, times 24 times 365. So this is few tens times few tens times few hundred. And now I have few times few, so I have 10 to the 1, okay, f 10 to the 1, 10 to the 2, f 10 to the 1, f 10 to the 2. So I have few times 1, 3, 4, 5, 6, 7. So few times 10 to the 7 seconds per year.
But that's really the pi is pi.
Yeah, just give me a second, okay? So this is just another way to use this 1 few 10 algebra. And then you could ask yourself, how accurate is this? Okay, so we said this is about 3 or something along those lines. If you want to know the actual calculation of what comes up, what did you say?
It's pi.
Pi.
3.15.
So pi times 10 to the 7 seconds per year.
Can you change marker?
What?
The marker. Sorry.
So maybe you go and, or somebody goes and they gets new markers because all of them are now not working so strongly. And so it turns out, you know, so this sounds probably pretty strange to you, right? Because what the hell, how did pi come about? So it's actually, so, you know, that's actually how I did it as well. I remember that, you know, we have pi 10 to the 7, but if you check the exact value, funnily it's quite close. Okay, it's very close to 30 billion seconds per year, but of course not exactly. You can just do the calculation. It would not come to pi, which is a transcendental number or whatever. It would never be exactly that, but it's actually pretty close. Good, but in any case, if you know that and you know 1 meter per second and you multiply that by few times 10 to the 7 seconds per year. So if you're walking at 1 minute and you have that, that's the number of meters that you'll do in a year. And that's actually also equal to the circumference of the Earth. So if you did walk 1 meter per second, which means, and you did it throughout the day and night, yeah, for the number of seconds in a year, 1 year and you'll go through the whole Earth. Okay, just another way to think about it. Good. So what did we cover so far? We talked about Fermi problems. In the homework that you'll get following this lecture, you'll get the opportunity to try and invent your own Fermi problem. Okay, so maybe that would give you some more, so you'll be able to think about this further. We kind of walked the Jesus trail. what I think is apparent to you also, that in terms of math that you need here, it's kind of like the math that you're supposed to know from basically junior high school. And I like it because I think that's sort of like the time at which our, things were, ingrained in us very strongly. And from there on, we learned all sorts of other things, but, we tend to forget them. At least, things from the more advanced math. We'll be using a few more things, but basically you need to multiply and divide, 10 to the something, and you're in pretty good shape. But what would differentiate you and others is like that actually you can do much, much more with that if you have the right frame of mind and capabilities, etc. Okay, so no need to be afraid of the math in the course. And now I'd like to go to another example. And through that, we're trying to learn. And this question we'll also take with us for the break. So what I ask you to try and do during the break, except for, enjoying the break, is try to infer how many trees there are in the world. Okay, so not to worry, you have about 10 minutes for the break. You only need to try and infer that, and I'll see you soon. Okay, so we want to know how many trees there are on Earth. Anybody has, maybe we'll start just with the punchline. Anybody has like estimates that they got? Yeah?
If you times 10 to the 11.
Oh wow, that's insane.
Anyone else?
Few times 10 to the 12.
Anyone else?
The same, like 10 times 10.
Okay, so there's actually a paper that came out recently. That gave the answer 3.04 times 10 to the 12.
Wow.
So, crazy, and also it's a paper in Nature from, a very well-known group. So, on the one hand, we have an answer, but now I'm curious, how can I check the answer? How can I tell if, it makes sense or not, and could I infer it alternatively? So this is what, I'm interested to see. So people that try to approach it, how did you do it?
We calculated the surface area of the, and then we divide it by. Yeah, you can.
Yeah,
We did it together. So.
Yeah, we calculated the surface area of Earth, then we deducted the oceans, and then we deducted about deserts and cities, and then what else?
And then we asked how many trees we have for
Square meters.
And there we didn't agree on.
Okay, so it sounds like you did again sort of like a divide and conquer approach. Where the components are on the one hand to infer what's the area of forest in the world and the area per tree, and then just divide the two, right? In order to do that, you went through the Earth surface area and continued from there. So let's try and follow that. How do we know the Earth surface area?
So we knew that the radius was written on the, and then we do 2 pi r squared. 2 pi r squared. Of the few square.
Okay.
That's for a circle, not for.
Okay. Oh, so let's think about it for a second. Okay. Yeah. Okay. So we want to do the Earth surface area, And we want to do something with an equation. Okay, so again here, by the way, I'll say there's like two ways. One is just to know the number. I actually also try to, I think that's also a useful thing to know. But if not, you calculate that. Good. But then, the thing of how to do exactly, is it 2, 4 divided by 3 or not? It could be sometimes confusing. So one way to approach it is just to see, in order to check whether it is like a, so you said, okay, you need, because it's an area, it needs to be r squared. But then, what are the prefactor, and you know that there's a pi somewhere, good. But then what should you have before? So one way to think about it, just I think is useful to, again, try to go back to basics in some way. What is the basic? You want to know you have a sphere, and you want to know the surface area. So now you understand it's a sphere, right?
We cannot say that. Sorry.
This is better?
Yeah, much better.
Okay, so you could think about it, just to verify if there's a 2 or a 4 or something like that. You can think about it that you just take the Earth, cut it in two, and just, let's say if you take one hemisphere, what would be the surface area of that? It would be at least like a disk, right? So I can think about it as a disk, not 3 dimensions, just as a disk. If it was just a disk, what would be the area? Okay, that I would hope we know. It's pi r squared, because that's the area of a circle. Okay? And now we have two sides of this. So we definitely have another pi r squared. But there's actually more to it than that, right? Because it's inflated and curved, right? So it can't be just 2, because that's just disks. You need to inflate it. And nicely, it just comes out. We could do do the derivation from 3D geometry, but it's just a factor of 2. Instead of 1 plus 2, it's actually with the sphere. It actually comes to twice that, so it's 4 pi r squared. Okay, but it's clearly not 2 pi r squared, just to be. And also maybe sometimes you get confused by dividing by 4/3, which talks about the volume. Okay, but this shows you that there's, even if you're confused, this like grounds you. Yeah.
If we're gonna use 1, few, 10 math, isn't like why do we even need that?
Yeah, we don't necessarily have to care if it's 4 or 3, but just because about the surface area of I wouldn't play with it, just with the equation. But it's true that we could do that as well, and we might even decide to do it. Okay, so you did 4 pi r squared. What did you do next?
We asked what is the length. We assume that the length area is divided by 3.
Okay, so if you plug those, we could also do it with 1 few 10, but I don't want to spend all of the day today doing that. This is about 500 million square kilometers. Yeah, and then you did what?
We divided by 3 because the ocean is like too.
Good, so you said let's go from that, which is the whole land, just to terrestrial, just the land area. So you divided that, gave you you divide by 3, so we have about 150 million kilometers squared. Good.
And then we say, roughly, we will say that half of that is trees and half of that is desert and cities and deserts.
Okay, good. So I like that approach. You're saying about half is forest, half is the rest. Okay. By the way, it's about 1/3. So it's actually good enough. Okay, so about 50 million square kilometers forest. Next.
And then we ask if you want to continue.
We asked what is the density of trees.
Okay, so just to be clear, up till now we're like in good shape in terms of what we need to do for the divide and conquer. We solved one part of the problem. Next.
How many square meters per tree?
Okay, so now the question is, how much square meters does a tree cover? Okay, how did you approach that?
I thought about myself walking in a forest. I said like a tree every 2 meters, so every 4 square meters per tree.
Good. So here's one way to get it to a value, and again, it's good to have some value. So otherwise, you're just left in the cloud. You have nothing. there's another cool way to do it, which I kind of like, when you try to estimate something that you don't know exactly what value to put, but you could just do an upper and lower bound and infer from that. What do I mean? Let's say I want to say what's the area that the tree takes. I could try and get like a lower bound. I'm saying no chance it's lower than that. Okay? What would be your suggestion for a lower bound? Let's try to get a lower bound.
Something
So if I had to say, I would say there's no, even if it's like a pretty dense forest, let's say 1 meter square, a tree every 1 meter square, that's like, clearly it's higher than that. Okay? So let's say lower bound would be 1 meter square. Okay. Now I need an upper bound.
So now we think about the sequoia.
Okay, so with the upper bound, also for the lower, like you could take like, the sequoia, some crazy, amazing tree, but what, we talk about the total number of trees in the world. So clearly we need some characteristic tree. We could think about something big, but still we're looking for something that would be realistic for the trees in the world. And I'm saying, I don't know exactly, but I would say 100 meters squared, which is, a bit more than this room or something. I think that, clearly, for me, my intuition says it's below that. Okay, so I'm looking for like an order of magnitude. Something like that, I would say, okay, it's below that.
But sorry, you need to know the surface area of a single tree. You could have a tree over there and a tree over there, and they will also cover one.
Right, but then I think it wouldn't be a forest. Like you could have a tree here and a tree there, but I don't think I'm trying to do it for forest.
Okay.
Forest, you have relatively good cover of it, okay? Okay, then you have a lower bound and upper bound. What do? Usually when you have two numbers and you want to get something in the middle, you take the average. How much is the average? Okay, so now it's interesting. Some people said 50, some people said 10. That's exactly the point. You could take the arithmetic mean, but the arithmetic mean is very biased by the big numbers. We could talk about it some more sometime. What you usually want to talk is what's known as the geometric mean. What's the geometric mean? It's one way to do it is just to say, it's take 1 times the other square root, which brings you to 10. Okay, it's like an upper bound, lower bound. You take the geometric mean, which is the center, but in log space.
I'd like to ask what is if we talk about scale, so it's the scale between.
Right, so if you think about it in terms of like, you call this 10 to the 0 meter squared, and this is 10 to the 2 meters squared, and the scale is like the exponent. The geometric mean is like the average of the exponents, which is 10 to the 1. Okay, so we have the size, the area of forest, the area per tree. You divide this by the other. Okay, you need to go from kilometer squared to meter squared. So we have 10 to the 6 kilometers squared. If you want to go from kilometer squared to meter squared, how much do I need to multiply?
Million?
Yeah, so you do need to multiply by million, but I would say that's also something that sometimes you get confused with. It's a bit confusing. So one way to not get confused is to know that you can always multiply by 1. What do I mean? I want to get rid of the units kilometers and move to meters. So I want to have here meter and to have here kilometer. And that I know very well. 1,000 meters is 1 kilometer. Okay, no doubt about it. Okay, and I have to do it twice. And then kilometers would fall with kilometers. I all have meters squared. So I have 50 times 10 to the 6. And then this is 10 to the 3 twice, so 10 to the 6 meters squared. Good. So basically I have few times 10 to the 10 to the 13 meters squared divided by 10 meters squared. And so the number of trees is roughly few times 10 to the 13 divided by, let's say, meters squared, divided by 10 meters squared per tree, which gives me this few times 10 to the 12 trees. Okay, so just to see what happened here, all we kind of needed to know is like the surface area of Earth, no big deal there, to make some assumptions. And you didn't have to be very accurate in them. You had to also know something about a tree. And there also you could take very general assumptions which make sense. And with that you have the superpower to know the number of trees, very close to the value that some people were able to publish a paper in Nature about. And finally I would say, which calculation do I prefer or believe more? Let's say this 3.04 10 to the 12 or few times 10 to the 12. What do you think?
Few times 10 to 12.
So it's interesting, even this was, published in a very high, respected journal, and this is, just published, online in the lecture that, would come, the recording would come online in the next few days. I kind of prefer this. I think it's more robust in many ways. I actually have to, wonder, how did the journal was happy with publishing this? Why?
It's very dynamic.
What do you mean?
Like trees can fall or pop up by the time it's published.
No, they would want to publish just because it's catchy. People want to see that.
You can't check, maybe. Like you can't count all the trees. So.
Yeah.
It's a precise number. The chance that they are really correct is very, very low.
Even though it's not a precise number. It's also basically saying few to 10 to the 12, like 3 or 4.
They also need to give the else for this number, and you just wrote the number.
Right, so I was very surprised that they put it in the abstract of the paper in Nature. I was very surprised they didn't give like an uncertainty range or an error bar, which I think is essential in order to get an uncertainty regarding the number. I think it's also true that it's a dynamic thing, and we could try and estimate how dynamic. When we talk about dynamic also, I try to go from adjective to so how much. So let's say to change this is sort of like within, how much is, this, place in after the decimal point as a fraction of the whole thing. It's like a bit less than 1%, right? So this tells us like it better than 1%. And now you can talk about how dynamic is the number of trees on Earth, and how much could it change? And I would say, it probably changes way more. Between when it was, when it was the work was done until when it was published, until when people read it, or something like that. Any other points about that? You could also ask. So this issue of how many significant digits you use is an interesting point. I actually. There was a funny example. I was in a conference in the UK, and I got this beautiful bottle, which I really like. It's like this very hardened glass and all that. And they also use numbers, which is nice. I don't know if you can read it, but this bottle can hold 1.572 10 to the 25 molecules of water, which is also kind of interesting to think. What did they think? But I think it's no coincidence. That this happens is, I think, in our society and also society, we have sometimes a lot of trust, like more trust in somebody that gives you more significant digits. It seems like they're more sophisticated, more accurate, etc. But I think it's kind of bullshit in the sense that, it all depends on the uncertainty involved. And actually, if you give too many digits, like here, it actually shows you're not very good at doing quantitative reasoning. Because you understand that, this number would depend, even on the temperature at which, if the air conditioning is a bit higher or a bit lower. So how could they, claim to know that? Not to talk about the fact that, how they produced it exactly, or how do you fill the water, or all sorts of other things would change that. But there's actually something else that nobody asked that, I'm confused, I'm surprised. Like, if you wanted to estimate, to write a paper on the number of trees in the world, you'll have another challenge in front of you, yeah?
Is it okay to neglect the amount of trees that are in cities, like parks and so on?
Okay, so you'll have to now start to analyze, whether you talk about cities or not. Okay, but let's assume that, they did it and, maybe they looked also at cities.
How do they verify?
How do you verify this? So actually, I think they did a very interesting work. They combined in this paper remote sensing from satellites together with measurements in situ, like in thousands of plots of land around the world. And they calibrated, what you get from here and what you get from there. So they had a way, and then you could do all sorts of, magic of, machine learning. You use some 80%, you learn about the 20%, you mix the whole thing, you repeat it a billion times, all sorts of things like that. But I'm curious about, like, again, if you want to estimate the number of trees in the world, I think you have more fundamental
What counts
challenge.
as a tree?
What counts as a tree, right? Like, how do you decide what's a tree? There's like a continuum of, of like plants. How do you decide what is a tree? Anybody knows how do you define a tree? Woody trunk.
That also, I don't know, I guess there's an actual family, but like then do you count palms as trees? They're actually just really big grass, but we would consider them trees.
Yeah, so it's actually nice. I didn't know that before I read that paper. There is a definition of a tree that, that is often used in forestry or also in that paper, is that when you stand next to it, it has a trunk.
Okay.
And at the breast height, what do you know?
It's a certain,
Yeah, so if you stand at the breast height, the diameter is at least 10 centimeters. Okay, you use that? Okay, good. Actually, I thought about it just that, like, it's a nice way to. It's like if you just this is 20 centimeters. Okay, so if you like do like this, if it fits, if it's less than that, then it's not considered a tree. If it's more than that, it is a tree. Okay, just a cool way next time, if you have a discussion with somebody whether you see a tree or not. Yeah.
The trunk needs to be. Or
the trunk at chest height.
Okay.
Yeah,
so
that's
it
yeah.
needs to be at least chest height, so a bonsai is not a tree.
Yeah, okay, so we could talk, we could get very sophisticated. Anyway, so what I want to say is that the issue of, you can infer things relatively easily and, then carry them in your head. But then also in terms of how you report numbers, it's also good to have some common sense in doing that. And you'll see also in the exercise, we, ask you to also follow that yourself when you giving estimates, to also think about how many digits you're using. And I think this is something also very transferable to your research. Doesn't matter if you're doing, what kind of research and what, apparatus you use in your experimental system. Very often they give you lots of significant digits, or maybe when you take the numbers and put them into some spreadsheet and do some calculations, you can get lots of significant digits. It doesn't matter, you should use all of them. Good, so we talked about trees, so we're done with that. I would say that maybe some of you are already feeling something that is very common in academia and in courses, known as the imposter syndrome. That, like, some people here, are more happy to, answer a question very quickly, and they have, like, and maybe they know about it, all sorts of things. And you don't know anything about it. You didn't have any idea what is the, definition of the tree or the radius of the earth, or what's the equation for the surface area. So I will say, this course is not about giving the fastest answer or something or something like that. It's more like, thinking, improving our way of thinking, and etc. And also I would say that, surprisingly or interestingly, almost it turns out from research, I didn't do it, but in the social sciences do such research, almost everybody in academia, say at the Weizmann Institute, probably feel that like, all the other students in the course or in the year or something like that are like really smart. Only they, they're mediocre, and they have a lot to improve and something like that. It's a very common psychological effect. So just be aware that, if you feel that, other people are also feeling that, and that's it. Even professors feel it, I could tell you. So in terms of the expectations for the course, so I think you now know a bit more about what's involved in the course. The way we're doing it, there's lectures. After, there'll be exercises where the exercises would be your way and to play around with doing calculations, with doing estimates, with thinking creatively about such things. And I think it's it's very important so that like the knowledge wouldn't evaporate the day after you finish the course. At the end of the course, you'll need to present a calculation on a question that's of interest to you in front of the class in 5 minutes. So the idea would be to take something like, how many trees are in the world, or a question that, fascinates you, like, you decide what it is. Maybe like some people did on, if they want to do a diet from drinking cold water, then they're burning calories in order to heat the water, whether it's a viable method to do it, or it could be something related to your research, or there's lots of different options to take it. We'll talk about it with time. So you'll be you'll get also the experience of doing that. If it's frightening to you also, you'll see that it's not the end of the world. And then you need to write a short vignette that's like a few pages long, something like 3 pages, of like saying, this is the question I decided to analyze. Here's why it's interesting. Here's the calculation that I did. Here is something I've learned as a result of that. And that's also an experience also in writing like a tiny paper, okay, like that's like few pages. And it's very much in the spirit of things, of like these short questions and answers in this course, in this book called Cell Biology by the Numbers, which I wrote a few years back with my colleague Rob Phillips at Caltech. And I was teaching a course on cell biology by the numbers, but then I decided to go not just cell biology, but biology by the numbers. I said, let's add sustainability. So it was biology and sustainability by the numbers. And this year I decided let's just do sustainability for the fun of it, so it would be open and relevant for everybody. So now it's sustainability by the numbers. I'll be passing it through anybody who wants. It's also available online if you write a book, Cell Biology by the Numbers. So you can see examples. And this is sort of like in the spirit of what you need to do. Question and few short pages to do some inference as a result of it. The lectures would be recorded and would be available online. At the same time, I expect people to be available to come to the lectures because a lot is happening in the class, and that's a critical aspect of how we do the learning and how we make it effective. So you're expected to come to all the classes. Sometimes you can't come because of one reason or another. In that case, we ask you to email us at the website email to let us know that you can't come beforehand. And after the lecture, after you watch it, you need to send us an email that says, what did you, something that you've learned from the lecture and something you suggest to improve in the lecture. Okay? It's a way to verify also that you're actively, listening, etc. Okay? The email of the...
Everyone has it in their inbox.
Yeah, so everybody have the email in the course, like cellbiologybythenumbers@gmail.com, if I'm not mistaken.
You got an email this morning, it was from that email.
So this is about, so the grade at the end of the course will be based on your participation in the lectures, the exercise that you've handed in, and the combination between the presentation that you gave and the short vignette that you wrote. Okay, so I can see there's like a few moving parts, but we did it before. It works beautifully. Great. So this is, I'd be happy to hear, if there's any questions about how this would work.
So the exercise on Moodle, or where do we find them? Yeah. And there is like a deadline I have to have them in.
Right. So you wanna?
No. So the deadline is usually before the next relevant lecture. So now you have 2 weeks for the next. You got a new exercise today. Congratulations. And you have 2 weeks to solve it. And that's until right before the next lecture.
And the next lecture is only 2 weeks.
No. Okay.
So the next relevant lecture specifically to that subject. So you have some free time. You do have a lecture next week. And then if you have like requests or problems or reserves, other issues, feel free to email us and we'll give you an extension.
It's going to be 1 to 2 weeks depending on the exercise.
Okay. So usually between the exercise given and the time you need to hand it in, either 1 week or 2 weeks. In this case, you have 2 weeks. Okay, which I think gives you ample time. If something is unclear, etc., feel free to write us also in the same email. Yeah.
Do we have 2 weeks because the next lecture in is something that we need to know to answer the current homework?
No.
No.
No, you can start working on it, immediately. I even highly recommend it, but you don't have to.
Very important, we are checking the exercises, so please hand them in very clear with a very legible handwriting, or
typed.
preferably typed. If we won't be able to read them, we will send them back to you to type them. Okay, so please don't do that. Preferably type them, or if you have a very, very clear handwriting, then
More questions or feedback or something? You could also, I'm always happy to hear feedback. So if anyone wants to stay, I'll stay for a few more minutes. If there's any questions or personal things, feel free. In general, I would say if there's, personal limitations, constraints, etc., we're open for that. We want you to succeed. I know there's many different things happening in your life except for this course. Maybe not as important, but also maybe, so really feel free to let us know, and we'll try to make it happen so that you end successfully and happily everything. And now I want to give you one final question. But people don't like the red for good reasons. What is how do you call it? It's not ratio. Okay, proportion, ratio. Between wild birds and domesticated birds, global biomass. Just a second. So I'm asking if I took all the birds in the world that are wild and put them on a weight, okay, I have a weight here, and I'm putting all the birds, something like that. I put all the wild ones, and I read, what comes up here, and then I do it again, but with all the domesticated, some other. Okay, what would be the ratio? Okay, would it be 10 to 1? Option A. Option B would be about 1 to 1. Option C, it would be 1 to 10. Question is clear?
I'm wondering about the definition of wild bird and the birds that live in the city. Like, because it seems like we have a lot of those.
Yeah. So what do you think?
A.
No, just not about the answer, about the question.
They're not domesticated.
They are not domesticated.
No.
Okay, so they're still defined as wild.
You can replace the word wild with unowned.
Unnamed, maybe.
Okay, who's voting for A? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
so which side is
No, A.
Which is bird?
A is wild, domesticated 10 to 1. Okay, again, re-election. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
Yeah, chickens are.
Chickens are domesticated.
Who's voting for?
Sorry, I'm not.
Who's voting for B?
Wait, but pigeons domesticated?
No, pigeons are
We have 1 for B. Who's voting for C?
I've changed my mind.
Okay, we have roughly the same number for A and C, and almost no, and 1 for B. So I think we have a good, two parties, and maybe the person in the middle will decide, who gets who's decided. So we'll learn more about it next time. Thank you very much.
Thank you.